we are going to do today and tomorrow the last section, and the last section from chapter 5. Try to find its number here. 5.5. And it's called the substitution rule. It's a biggie. When you, I think it's a bit shaky today, so there we go. Up to this point in time, we've been finding antiderivatives, and the main theme that kind of held them all together was, couldn't we find the antiderivatives because they were on this table? So if it looked like that, we knew it was a tan. If it looked like that, we knew it was in e to the x. And that one's a rule, but if it was x cubed or x squared, we could get it. But you can imagine that there are many, many functions in the world where no matter what algebra you do, right, you can't factor it, you can't use a trig identity, you can't do anything to it that's ever going to make it look like this. There are lots of situations where that is just not going to happen. There's an example of one. Can you trust me that you do not know how to get the antiderivative of that because it doesn't fit any of these? You can't do any algebra to that that will make it one of these. So the first time these kind of problems arise, I'm sure there was two main ways of tackling it. The first way they tackled it is they said, can't do it. Why are you giving me an impossible question? I can't do that question. Let's just throw it away and pretend it's not there and get on with our lives. And then the other group of mathematicians said, nah, I'm not going to just settle for it can't be done. I'm going to figure out a way to do it. And we're going to do what's called the substitution rule, which is a really sneaky way of getting around how do you find the antiderivative of functions like this. And it adds a number of steps. The first step, in fact, I've already written them because it was mother class, so I could put them there while I talk through them. This is how you use it. The first step is you choose a suitable U substitution. Not telling you what that is yet, but that's what you're going to do. Essentially, you're going to take this and you're going to turn it into another integral that you do know how to get the answer to. So you're going to use substitution, right? Replacing the x's, whatever, by other things, right? And convert it into a new integral that's the same value, but in terms of a different variable. And this new integral has a very nice property that I do know how to get it because it's one of these. Step 2, you convert all the terms in your original integral so that they now are in terms of the new one. Step 3, find the answer. But when you find the answer in step 3, the answer will be an antiderivative, but it will be in terms of this variable called u, not the guy you want, x, which is why you have step 4. Convert your answer back to being in terms of x. So we are going to go through a number of different steps, but when we're finished, we will be able to get the integral of this guy. Now, step 1, I'm just going to tell you, but we're going to get practice at figuring them out. I'm going to tell you who this substitution is going to be. We call them U subs for short. The U sub we're going to use is U equals x cubed plus 5. Not telling you why I'm picking that, but I'm picking it for right now. What you then do is you differentiate this function with respect to x. And yes, you are going to be doing an awful lot of differentiation in this section. So Calc 1 is now your friend. So hopefully you're good at differentiating. This fella, this notation is the derivative, right? du by dx, it's the derivative of u with respect to x. This is a reason why this notation is actually used. This is one of its major uses. Isn't that a little bit like, I know it's not cross multiplication, but doesn't it algebraically look very similar to cross multiplication? And you keep going until you get the dx on its own. So you'll have a u sub, and you will always find its derivative in these types of questions with respect to x. You'll do this thing I call the crossover, and then you isolate the dx. Now, once you've isolated the dx, you return to this question. I'm just going to move it over here because I need more room. And you start replacing things. That x cubed plus 5 in the bottom becomes a u. That x squared is still x squared for a little while, not for long. That dx is now going to be 1 over 3x squared du. Now, something really quite amazing and very cool has happened. Do you notice that that x squared is going to cancel out this x squared? And that means that we now are left with essentially 1/3 1 over u. I'm emphasizing the 3 there as a third. So we have taken this integral with x cubes and x squareds that we don't know how to get the answer, and I've turned it into this guy. Don't worry about the third, that's just a multiple. What's the antiderivative of 1 over u?
Natural log u.
Natural log of u. Now, to keep the back of the book happy, will we stick an absolute value around it just so that they don't get annoyed at us? Because when you type the answer in, it seems, because I had a look at some of their solutions, that they do that. Oh, and by the way, sometimes they don't, which really annoys me. If they're going to do it, just do it all the time. And if you're not going to do it, then just not do it any of the time. But this, sometimes you do it and sometimes you don't, is really a bit of a nuisance. And I think I know why they can sometimes avoid it, but I don't think it's worth the effort. Now, have you noticed that this is the answer to the antiderivative that we're after? But it's not in terms of what we want. Don't we want the answer to be in terms of x's? So what I call step 4 is now about to happen. This here, this line here is basically step 3. So step 4 is convert your answer back into x's. Well, instead of being 1/3 the natural log of u, u is x cubed plus 5. So we now have that guy. So the antiderivative of this function is 1/3 the natural log of x cubed plus 5, I'd say. Do you see, we now have a technique, provided we can find a good u sub, right? One that works. Don't we now have a technique that allows us to find antiderivatives of even more complicated functions than we did yesterday or the day before yesterday? Right, Kathy, I know that you've been tackling these guys. There's another way to do this called the UDV method. Is that the one you're using?
I don't think so. I think I'm using
Okay, good, because I'm not going to show anybody that method. So is this the technique that you've been using? Perfect, great. Some textbooks go left and some textbooks go right. If I'm going left, you know, the UDV method, which I'm not even going to mention because I don't think it's worthwhile for you to learn 2 different techniques to do the same question. And the reason I don't think it's worthwhile is what tends to happen in some people is that they don't use the left technique and they don't use the right technique. What they do is they make a Frankenstein technique made up of a bit of one and a bit of the other that never works any of the times. And, you know, if one method works, use it. Why do you need a second? That does not mean that if you do not like this process, that you do not go online and look for the other way of doing it and decide on your own that you like it better, in which case you would do it that way, I guess. Suppose I added one more step to this question. This is an indefinite integral, right? Because it's got plus c. This is called a definite integral because it's got limits. Wouldn't the only difference be that you'd lose the plus c and you would do 1/3 the natural log of this guy evaluated at x equals 0 to x equals 1. Right? So it's not that you would do anything that different. Wouldn't you just do what you would have done anyway once you know the antiderivative? If you plug in 1 here, you get 5, so it's 1/3 log 5. And you plug in 0, 6, sorry, 1/3 log 6. If you plug in 0, you get 5. And I don't need to stick an absolute value around 6 and 5 because aren't these just 6 and 5 anyway? So we're doing a little skill building exercise now. I'm going to show you lots of integrals. And the only thing that we're going to do is pick who a good u-sub is. So I'm going to show you how you pick u-subs, because if you can do that, it's a bit like a shopping list, isn't it? You do this, you do this, you do this, you get the answer, right? So if you ever get an integral where there is a bracket with some ugly stuff inside it, raised to the power of 2, 10, or 1,000,000, like this, in those situations, you will choose, do another line here, you will choose a u-sub to be whatever is inside the brackets. Okay? If you have a fraction, your typical u-sub will be the denominator. Now, the rules I'm telling you right now are truisms in the sense that 99% of the time, they are exactly going to work. I'm not going to show you the special cases or the exceptions to these rules until tomorrow. But right now, the vast majority of situations, that rule that I've just given you applies. Now, there are two possible u-subs in this question. You either pick the thing inside the brackets, right? The ugly thing inside the brackets, in which case the u-sub will be 2x squared plus x. The alternate u-sub is the entire denominator, including the power of 10 thing, right? The entire bit. Only one of them will actually work. The other one will just take you down a rabbit hole that goes nowhere, right? So what u-sub do you think I'm going to pick? The entire bomb or just this piece of the bomb? You get a 50-50 guess. If you feel lucky, go for one of them.
The entire denominator.
Don't go to Vegas. Only use the guy inside the ugly bracket. But don't worry about getting that wrong, because there's no reason you should, at this stage, you should actually know that. But will you use that as now a rule? If you've got a fraction, but the bottom contains an ugly bracket to the power of 10, the ugly bracket to the power of 10 overrides the rule that you use the bottom, right? The denominator. What about square roots? Well, whatever is inside the square root is your use of. What about weird trig functions? Cosine the ugly guy, sine the ugly guy, you know, tan the ugly guy, secant the ugly guy. What do you do as a u sub in those situations? Well, the answer is the ugly guy. What about e to the ugly guy? See if it's not an x. To me, that's I call them the ugly guy, right? E to the x is e to the x. E to the sine x is e to the ugly guy, right? If you're wondering what the ugly guy means, it's just a name, right? Here we have an e to the ugly guy. Whenever you see e to the ugly guy, your u sub will almost always be the ugly guy. Are you beginning to get a feel for who the u sub should be in certain circumstances, right? In these particular ones, who the u sub should be rather than some other choice. Okay, so I'm going to, hold on for a second, I'm in the wrong place. I'm getting paranoid about Zoom lately. It's been, I think it's you lot's fault. Just something, I don't know, something weird's going on. But it doesn't seem to happen with my other class, so go figure. Who should the u sub be for that question?
X cubed plus 27.
I like it. I'm just picking randomly some questions from the book. And sometimes you just have to trust the math. Because this one is, I mean, as ugly goes, this guy is ridiculously ugly. But this time we have a choice. Cosine the ugly guy or the denominator, right? That's the choices. So is it going to be pi over x to the 47, right? That's the ugly guy inside the cosine. Or is it going to be the x to the 48? To me, that's the only two realistic choices. That's a bit of a guess now, because we haven't done that combination. Although we have done one very similar to it. What do you think the u sub in this one will be?
Pi over x to the 47.
Correct. Oops. Have you noticed that the denominator choice never gets chosen if there's another choice instead? And that's pretty typical. Just so that it doesn't feel too left out. What would the u sub be in this question?
4 plus x to the 10.
Yeah. Isn't that the kind of one of the few times where the denominator is actually the u sub? Right. If I called that guy the sine of x to the 9 or e to the x to the 9 or the square root of some weird stuff, wouldn't that then take over as being the probable u sub? Right. So when it's just a fraction with nothing particularly interesting on the top, that's typically when the denominator is going to be your u sub. If anything else happens, nah, it's probably the other choice. So let's do the whole process now from start to finish. So I got this one, I might as well start with it. X squared, x cubed plus 2 dx. First question is, choose a u sub. So who am I picking?
X cubed plus 2.
Because it's inside the square root. Agreed? Now, swollen pens all over the place here. Once you've got your u sub, you go through this stage. It's the same process every time. Differentiate with respect to x. What I call the crossover, which is basically similar to cross product, right? And then isolate the dx. In this case, if you divide both sides by 3x squared, you get that. So when you get to the point where dx is on its own and it's equal to a horrible mess, you know you're finished the algebra that goes here, right? You then come over here, and if you don't know what to do, like I don't know what to do to x squared, just write it down as x squared. It'll sort itself out later. Won't this become the square root of u? And the dx will get replaced by 1 over 3x squared du. Now, if you've done it correctly, don't you get that little magical, oh, that's cool, that any x's that happen to still be there, at this point in time, shouldn't they be killed off, typically? And in this case, I'm calling this 1/3 the square root of u du, which I'm kind of happy with. Would you agree that is a doable question? Now, I would have to do just a little bit to it, because I'm going to have to find its antiderivative. Would it make sense that I better call it u to the half so I can, you know, do the power rule? Now, if you add 1 to the power and then you divide by the new power, you get that guy plus c. Unfortunately, hopefully you won't be one of them. A lot of people write that into the box. Hey, I've done it. But remember, you still have convert back. So 2/9 x cubed plus 2, because that's what u was equal to, all raised to the power of 3r's, I'd say. And as far as web assign is concerned, they will accept that as a valid answer. And so if you type it in, there's nothing I can do to stop you. It's going to be, you'll get the points, and that's fine. But can I tell you that really this is a better version? This is the style point version of that answer. And why is mathematically this considered a better version of the answer than this, even though they're equivalent mathematically? Why is this considered a better version?
Doesn't it go back to the beginning, which also had the square root in it?
Yeah, and there's a rule that says, basically, I call it style points. Style point says it's got to look the same as the starter. There is an advantage to this over that, not just the fact that this is considered a better format. If this up here was actually a specific definite integral. Can you see that virtually nothing changed in my working, right? But when I just have to plug 1 and 0, would you agree that it's easier to get exact values when you have square roots than when you have 3/2? Because 3/2 is a bit weird, and you're not always going to recognize what that is when you write it out in its full format. Well, if you plug 1 in here, you get 1, and that's 1, 2, you get 27. So it's 2/9. So 3, 3, 3, 27. And if you plug in 0, you get 2/9 and 8. Now, you see the square root of 27, the square root of 8 are much nicer than 27 to the 3/2 and 8 to the 3/2. Would you agree that most human beings that makes sense? Now that I've done that, is there anything I can do to these that makes them even nicer looking? What's the square root of 27 if you simplify it a little bit?
3 times the square root of 3.
And the 3 and the 9 will cancel. So you'll get 2/3 root 3. And in this one, don't you get 2 root 2, which is not so nice. And that would be like the ultimate, you couldn't do any better answer. We cool? So far, so good? Right. Choose another one. Not much happening here. Nothing much happening here. Yeah, let's pick that one. God, that's ugly. The cosine of this ugly fraction all over x to the 48. And somehow or other, we're going to find its antiderivative. That's going to be pretty amazing if we could get that right. Decision 1. The biggest decision is always going to be picking the correct U sub. If you pick the wrong U sub, you spend 5 minutes and you'll know pretty much by the time you get halfway through it ain't going to work. And the reason you'll know it's not going to work is there are going to be some x's left over that you just can't get rid of. And that's normally a sign you've picked a bad U sub. So what U sub should I choose in this world?
Pi over x to the 47th power.
Yeah, nobody would like that, but that's what you have to pick, right? It's not a very nice looking U sub. I'm going to change it into this fella. And the reason I'm doing that is, don't I need to differentiate it and I need to use the power rule, so it has to be written as a negative power to do that. So differentiate then with respect to x, and you get negative 47 pi. Oh, I could just see a mistake here, and I stopped myself, so I know I might have made that mistake if I hadn't. You multiply by the power, right? And then don't you reduce the power by 1 when you differentiate? So what's the new power of x?
Negative 48.
Perfect. If you take 1 away from negative 47, isn't it negative 48? Do you know the mistake I just caught myself from doing? Negative 46. Can you see it almost sounds like it's right, but we know it's not, right? Now, this fella here, algebraically, is very messy. So I'm going to rewrite this negative power as that. Now, when I do my little cross multiply thing, which I just call crossover because it's not really cross multiply, if I do that, I get x to the 48 du is negative 47 pi dx. You see a little crossover thing? And then to isolate the dx, won't I have x over 48, a negative, and a 47 pi with a du? You see how messy the dx is, right? It's got negatives and fractions in it. Over here now, the cosine of ugly guy becomes the cosine of u. The x to the 48, I'll leave that alone for a minute. The dx is going to be replaced by a negative x to the 4 over 47 pi du. And that's an 8 there. And then by magic, they cancel. And so we have a negative 1 over 47 pi cosine of u. I don't like that, but that doesn't matter. Isn't that just a weird number? So aren't I really just integrating cosine of u? Okay, be careful. What's the antiderivative of cosine u?
Sine u.
Yeah. And so positive means that the sign doesn't change. Would you agree it's that guy? And then remember, as we always should, to return back to the original. If we did not have the substitution method, right, if just for some reason nobody ever thought of this trick, this algebraic manipulation trick to make this happen, would you agree that I don't think anybody could take this and just miraculously guesstimate that that would be its antiderivative? I mean, could its antiderivative been all sorts of other things as well? I know it's not, but couldn't it have been? So the quest of finding antiderivatives has now got much more difficult, because we are now going to be spending a lot more time dealing with situations where we don't just use our basic antiderivative table, but we have to use techniques, one of the most important of which is this one here called the substitution rule. Give me a U sub.
2x to the 9th plus 1.
Agreed. So now I will differentiate it with respect to x. I'll do the crossover. And then I will isolate the dx. Okay, that was pretty typical. Just going to leave the 4x to the power of 8 for a minute over u times 1 over 18 x to the 8 du. Nice cancel. Can I take care of this a little bit and call it 2/9 as well? So what we're looking at is 2/9 1 over u du. Okay, what's the antiderivative of 2/9 1 over u?
2 nice natural log u.
A little bit louder, please. I heard the 2/9 part, but not the rest.
Natural log u.
I hear you. And to finish with, you know, I'm perfectly happy with that answer. What do you think I might have to do to make WebAssign happy?
Absolute value.
Yeah, so right. Any questions about that? The more practice you get at doing this substitution technique, right, the more, hopefully, the more confident you'll be in picking a good U sub, and then the algebra of what you do, you know, to make it look pretty, antiderivatives, and then off you go, and you're finished. Let's pick something else. Just to prove to you that there's no reason in the world why integrals need to always be x's. Can you have integrals with t's and p's and w's, and who cares? So it's still going to be called a U sub. What is the U sub in this question?
1 plus cosine of t.
1 plus cosine of t. Agreed? So when you differentiate with respect to t, do you get plus sine or negative sine t?
Negative sign.
Negative. Because we are differentiating. Do you see the problem here is that sometimes you're going to be integrating a sign and sometimes you're going to be differentiating a sign. It depends on what you're doing, whether the answer goes positive or negative on you. So differentiating a cosine generates a negative sign. Now the crossover, and then in this case, you're going to have to isolate not the dx, but the dt, right? Does the same job. So we're going to have a sine t, a square root of u, a negative 1 over sine t, and a du. That's a good thing, you see. Typically, if the original integral turns into an integral that's number 1 simpler and number 2 only has u's in it, isn't that a good sign that you've been doing the right process? Right? There isn't a t squared left over. Or it's not some really weird, ugly,
Yeah, you are.
worse one. Now, I'm just going to put you on mute because you may not want everyone to hear that conversation. Right, so back to what I was saying here. Are we good so far? Is there anything I need to do to this integral so I can keep going? Because it's maybe not in a form that's going to make antiderivatives easy, is it? Okay, what should I write down then?
Do the square root of u to u to the 1/2.
Okay. And now I can use the power rule, great. So the power rule is add 1 to the power and divide by the new power. I like that version. And then just replace by 1 plus cosine t and you are done. You will also find that that's the same thing. But that's style points, and that's just correct. So that's correct and got nice style points.
Could you move the paper up a little bit? We can't see it.
Oh, sorry. There we go.
Thanks.
So this is a guy, and I turned it into this fella when you replace the u by 1 plus cosine. I'm just saying that you may find that this is also an acceptable answer as far as WebAssign is concerned. I don't know if that's a feature of WebAssign, that it either can't cope with that or that it allows both answers. So somebody might want to do that for me, because I can't use WebAssign the same way that you can, because I'm in charge of WebAssign. I don't get to do the questions. It seems a bit strange, but I don't. So if somebody could do a question like that and plug in both their, plug in this answer, and if it takes it, tell me tomorrow, yeah, it takes the style point version, then that way I'll feel much more comfortable about pushing the style point version. But if it's really annoying, and it could do this, it might only accept this and not accept that and tell you this is wrong, right? So that is an issue if it does that. Are we good? And time to move on then. What else have we got? Well, we get time for one more. Yeah, why not? Oh, I'm using P today, I think. Okay, I need a U sub.
2 minus e to the p.
I like it. Not the whole bomb. Not the whole thing, power of 10. Bad U sub. Only this piece, right? Remember, we've done a couple examples where what happens if there's a choice? Don't pick the denominator is your answer, right? Pick whatever the other choice happened to have been. Right, in this case then, if you differentiate with respect to p, you will get negative e to the p. And the crossover, you will get negative e to the p dp. And then when you isolate the dp, you get negative 1 over e to the p du. So I have e to the p, I have u to the 10, I have a negative 1 over e to the p, and I have a du. And perfect. So I am now looking at negative 1 over u to the 10 du. That's where we are. We always have algebraic decisions to make in questions. Sometimes the way it is isn't the way it needs to be to enable us to progress here. This is one of these situations. How will I rewrite this so that I'll be able to find an antiderivative?
U to the negative 10.
Agreed? Yeah. Now, add 1 to the power. I'm not going to make the mistake this time. Negative 9, agreed? Add 1 to the power. Divide by the new power. Dividing by negative 9 is like multiplying by negative 1/9. 2 negatives make it a plus. Are you happy about where that positive 1/9 ended up coming from? The 2 negatives cancelled out in 1 over 9. That in turn, I'm going to write it like that. I probably should have moved the 1 along a little bit. And now I'm going to convert it to 2 take away e to the p all raised to the 9, add C. Or it might be the equivalent, which is that guy. This guy and that guy are the same guy. I think this is a time for you to say hi, so you want to do the attendance thing. And while you're doing that, are we good? Any questions before we finish off today? Now, you're going to have to go back and maybe watch the video that replaced the day that was missing. If you find that you're coping well with that homework, then maybe you won't need to look at it that much. Maybe you only need to look at the last 10 minutes, whatever. But it is there if it's something you need.